All right. Last time, we were working in section 4.1a. And 4.1a was about the idea of intervals of concavity and finding these hypercritical points called, and these idea of the points of inflection. So, here's the big deal on this material. So, when you're talking about intervals of increase and decrease, what do we do? To find intervals of increase and decrease, the first thing you have to do, what's my setup? The first thing I'm going to do is I'm going to take my derivative, I'm going to set it equal to 0 and solve, and don't forget, it's also where the derivative does not exist at. These are called, when you find this guy and solve, these are called the critical values, right? And then to find intervals of increase and decrease, what do? Then I draw a number line with these critical values on the particular number line, but it was a number line for the first derivative. And when it was the first derivative was positive, that meant you were increasing, and when the first derivative was negative, that meant you were decreasing, and you got your, quote, intervals of increasing and decreasing. And it was called the first derivative test. It also told us one other thing. What kind of point did you have at your critical value? In this example, since I increase and then I decrease, it actually makes that critical value a maximum. So we're still very interested, even in chapter 4, this idea of maximizing, minimizing. That is paramount. Think about the business concepts behind that. Maximizing your profits, minimizing your costs, so forth and so on. So that being said, now, that's all chapter 3 stuff. Here in chapter 4, we're going to be talking about intervals of concavity. Now, intervals of concavity is when you basically, when it's concave up, it'll be U-shaped up, and when it's concave down, it's going to be U-shaped down. So we're talking about how the U-ness of the graph is going to be U-shaped up versus U-shaped down. Intervals of increase and decrease just means going up versus going down. Okay? But look at the steps and the patterns. Now, if I figure out my intervals of concavity, what I'm going to do here is I'm going to take this second derivative, set it equal to 0 and solve, and also, and where the second derivative does not exist at. And where does a second derivative, just like a first derivative, where does it not exist at? Well, remember, you can't divide by what number? 0. So if you all of a sudden your function starts showing up in the denominator after you took its derivative, you should pay attention to, hey, what point makes this derivative not exist? Divide by 0. That's what you're really focusing on, and that does not exist. Now, with this intervals, anytime you hear intervals, you know you're going to draw a number line. So this will be a number line, and this will be a second derivative number line. Now, when you take the second derivative, set it equal to 0 and solve, and where the second derivative does not exist at, you're going to get a point. I'm going to call him B. They were called the hypercritical values, also known as possible inflection points. Okay? So I'll keep using that word inflection but to be an inflection point, officially you have to change concavity. You've got to go from negative to positive or from positive to negative. You actually have to have a sign change on this thing. And you're going to do the same thing. What we did up here was we did test values at particular points. And we did test values at particular points to see if they're going to be positive or they're going to be negative. You're going to do the same thing here, but you're going to do it in the second derivative. You're going to do a particular test value of a point in there, and let's say it's going to be negative, and you're going to do a test value over here plugging into the second derivative, whatever the point happens to be you pick. It's going to be positive, so this will be negative. This will be positive. So it's looking exactly the same thing, except with a being a second derivative, this is going to be concave which way? Down, and this interval will be concave up. And so you're going to answer the question once again in interval notation using parentheses. Does that make sense? Now, this is the idea behind section 4.1a. In section 4.1b, we're going to be focusing something called the second derivative test. Now, in the second derivative test, here's the deal. We're still interested in identifying max-min points. It's still all about local max versus local minimum points. Maximizing something or other, minimizing something else. Maximizing, minimizing. But here's the deal. When we did it way back here in chapter 3, we actually had to analyze the number line. That was my first derivative test. This is going to be called the second derivative test. In the first derivative test, when the function went up and the function went down, it made A an actual local maximum. And if you go down and then go back up, that makes a local minimum at your particular critical value. Does that make sense? Now, what the second derivative test does, and it's a little bit better, you don't actually have to use a number line. So once you get your critical value, now, remind you about a critical value. The critical value occurred when the derivative was equal to 0 or where the derivative does not exist at. Set derivative equal to 0 and solve. Now, here's the big deal about maximum minimum. So let's say x equals a is your critical value. This is called the second derivative test. The second derivative test says this. Take your critical value and plug it into your second derivative. So you've got two cases. Case 1. If the second derivative evaluated at your critical value is greater than 0. Now remember, A is a max-min point. But which one is it? You got a 50-50 shot on this thing. The second derivative will tell you. If the second derivative, which measures concavity, is greater than 0, what kind of concavity do you have if it's greater than 0? It's going to be concave up. But if you've got a critical point, where does that critical point have to be at? It's going to be on the bottom, which makes x equal a local minimum. Does that make sense? And case number 2, when you take your second derivative and evaluate it at your critical point A, and if it happens to be less than 0 means what? What kind of concavity do you have when you're less than 0? That's negative, which means it's going to be concave down. And I'm drawing these pictures because I know you're thinking positive should be max. No, positive means it's U-shaped up, which puts the actual critical point at the bottom, makes it a minimum. And when it's negative, the second derivative is negative, it's concave down, which would put your critical point at the top, which means x equals a is going to be a local maximum. But when you look at this, you go, well, great, I could have found the same information from my number line on the intervals of increase and decrease. You're right, you would have. But notice, with this information, I actually don't have to go out of my way to draw a big number line picture on this thing. I found my critical points, and then I just evaluate them at the second derivative, and based upon the sign of the second derivative, I can tell you immediately if it's going to be a max or min. That's called the second derivative test. It's just still just try to identify maximums and minimums. Does that make sense? Don't lose you guys anywhere. All right. So, if you go back and look at your notes, we didn't quite finish up section 4.1a. I got to this point right here, and I didn't get to B, and I want to do 4 down here, and then we'll move on to section 1.4b. So, here we go. Look at the question number 3 here. It asks you for this. Determine the intervals in which the function is concave up and concave downward, and locate all points of inflection. And remember, an inflection point is the points where you change concavity. If you don't change concavity, you're going from negative, and then you go more negative after you hit your hypercritical value. It's not going to be an inflection point. You're going to go from negative to positive or from positive to negative. So, to actually find these hypercritical points, because we need those for the concave up, concave down stuff, I got to go for the second derivative. So here we go. First thing I'm going to do is clean up my functions. I don't do a cube root. What's a cube root? Very good. So there'll be 2x plus 3 raised to the 1/3 power. Now I'm going to take the first derivative. What rule am I going to use to take the first derivative? Chain rule. Derivative the outside, inside stays the same times derivative the inside. So this is going to be 1/3 times 2x plus 3, subtract 1, raised to the negative 2/3, times the derivative of the inside, which is 2. But you've got to clean them up before you take another derivative. So cleaning this guy up, I'm just going to put my consts together. 2 times 1/3 makes it 2/3 times 2x plus 3 raised to the negative 2/3 power. Okay? Now, let's take the second derivative. Now, 2/3 is a constant. When you multiply a constant times a function, constants hold over. Now, look at this function. This is 2/3 times 2x plus 3 raised to the negative 2/3 power. Once again, that's chain rule. So hold that 2/3 out front and take derivative of something to a power. Chain rule, you take derivative of the outside, so the negative 2/3 comes out front. The inside 2x plus 3 stays the same. Subtract 1, that'll give you negative 5/3 times derivative of the inside, which is 2. Cleaning this guy up, my second derivative is going to be 2 times a negative 2 times a 2. It's at negative 8/3 times, excuse me, 3 times 3, that would actually be 9, negative 8/9, excuse me on that, times the 2x plus 3 raised to the negative 5/3. But I want to clean them up even more, because this is the guy, my second derivative, to find my hypercritical values, these possible inflection points. I got to set this guy equal to 0. Where does a negative exponent put you? In the denominator. The 9 is already in the denominator, so this would be officially negative 8 over 9 times 2x plus 3 raised to the positive 5/3. So there is officially my cleaned up version of my second derivative. But now, I'm going to set him equal to 0 and solve. How do you solve when you have a fraction equal to 0? What do you do? Every time. Well, okay, you're jumping way again, but you're on the right track. First thing you do to solve this thing is you're going to multiply both sides by your denominator, right? Clear denominators. But when I multiply both sides by my denominator, multiply both sides by 9 times 2x plus 3 to the 5/3 on both sides, I end up getting the 9, 2x plus 3 to the 5/3 end up canceling. That ends up giving you negative 8 is equal to, and 0 times anybody is 0. But does negative 8 equal 0? No. So there's no solution here. But we're not done. Because it's a fraction, so there is no solution when I try to take derivative equal to 0, my second derivative equal to 0. But this is a fraction. I do have to worry about where the second derivative does not exist at. Where does the second derivative not exist at? It's when that denominator is equal to 0. So I'm going to take the denominator, which is that 9 times 2x plus 3 to the 5/3 power, set it equals 0. Solving, I'm going to divide by 9. Pretty much cancels there and gives me 2x plus 3 raised to the 5/3 equals 0 divided by 9 is still 0. What gets rid of a 5/3 power? Well, the basic 5/3 means you're going to raise it to the 5th power and take the cube root of it. But to do the opposite of that, you raise it to the reciprocal. What's the reciprocal of 5/3? 3/5. What I do to one side, I do this. I'm going to raise both sides to the 3/5 power. But 0 to any power is 0. So pretty much you set inside the parentheses the 2x plus 3 equals 0. Because 5/3 to the 3/5 power to a power you multiply, that'll end up being 1 because everybody cancels. Anything to the first power is himself. Now solving for x, no problem here. I'm going to subtract 3, and then I'm going to divide by 2, so I get 2x equals negative 3. Divide by 2, I get x is equal to negative 3/2. This is where the second derivative does not exist at. Does that make sense? Now, I'm supposed to find intervals of concavity. Intervals means what? I'm going to draw a number line. And I'm going to come down here to this problem. I'm going to draw my number line. And this is going to be a second derivative number line. And I got to put my hypercritical value, this impossible inflection number on my number line. So here it is right here. Here's negative 3/2. And now, slide this thing up. Now I'm going to do test values in the second derivative. So I'm doing the exact same thing as what I was doing before. Pick a number less than negative 3/2. Remember, negative 3/2 is like negative 1.5. Something less than that would be like negative 2. So f double prime of negative 2. So I'm going to take negative 2 and plug it into my second derivative. This would be equal to negative 8 divided by 9 times 2 times negative 2 plus 3 raised to the 5/3 power. And I'm just going to save a little bit of time here, and I'm going to put that on the old calculator for you guys. And so when I do that, it'll be negative 8 divided by parentheses 9, another parentheses, 2 times negative 2 plus 3, close parentheses, raised to the 5/3 power, and then over arrow, close parentheses for the denominator. So that's just me typing in exactly the way it looks. I just wanted to kind of show you guys this on the calculator with that negative 8 up front. And personally, I don't care what number I get. What I care about is the sign. What do I get? I get 0.8889. Who cares what the number is? It's positive, so everybody in this interval is going to be positive. Now I'm going to pick a number bigger than negative 3/2, which is negative 1.5. Take a wild guess and use your brain. What I'm going to use? Good choice. 0. And plugging in 0 into this thing, that'll be negative 8 divided by 9 times 2 times, and place that negative 2. I'm going to put a 0 in there, plus 3 raised to the 5/3 power, and I end up getting negative 0.1424 something or other. I don't care what the number is. What's the sign of it? It's negative. That means it's negative. But this is where most students are going to screw this up. They're automatically been programmed. I'm going to increase here, decrease here. No. This is the second derivative. What does this tell me? Not about increase and decrease. It tells me about concavity. So I am concave up here, and I'm concave down here. So to answer the question, where am I concave up at? Give me the interval. And where am I concave down at? Give me the interval. And again, on Hawks, you're going to sit there and type in parentheses. It's going to be an interval answer for intervals of concavity. So I'm concave up. This arrow represents negative infinity. So it'll be from negative infinity to negative 3/2. And I'm concave down from negative 3/2 to infinity. Does that make sense? One other last thing, because they ask lots of questions, lots of problems on this one. They ask you also this. Locate all points of inflection. Is this, quote, hypercritical value thing here, is it actually an inflection point? Yes or no? Is this an inflection point? Why? Very good. You changed sign. You went concave up to concave down. You changed concavity signs. That's what makes inflection points. So, inflection point, question mark, yes. So, and the point, the x-coordinate is negative 3/2. This is an inflection point, and 3/2, but I need a y-coordinate. How do I get a y-coordinate? What do I got to do to get an inflection point? Plug it into the original equation. And there's my original equation, which is the cube root of 2x plus 3. Plugging in negative 3/2, no problem. 2 times negative 3/2 is actually negative 3 because the 2's cancel. Negative 3 plus 3 is 0, and the cube root of 0 is 0. The point is actually negative 3/2 comma 0. Does that make sense? And it is an inflection point because you changed signs on your number line in terms of your concavity. You changed concavity. So answering the questions, this was one of the questions, and the intervals of concavity was the other answer to the question. Does that make sense? Now, on this particular problem, number 4, you're supposed to, and you're always in trouble when they tell you personally to give an example, but there's actually only one of these examples that's going to work this problem because you're going to have to outthink it. It says, give an example of a polynomial function which satisfies the condition. F of 5 equals 15. F prime is not 0, but F double prime is 0. How in the world, what kind of function am I going to take the derivative of that says that when I finally take the second derivative, I'm going to get 0? Let's think about it. Derivative of what is 0? So if I want this, you got it. The second derivative is equal to 0 implies that the first derivative had to be, I'm going to call him C for constant, right? Because we know, I don't know what the constant is, well, not yet. So the derivative of a constant is 0. Does that make sense? So if the second derivative is 0, that automatically tells me the first derivative had to be a constant. And to be able to get a first derivative to be a constant, what does the actual function have to be? The derivative of what is a constant? Very good. Constant times x. Remember, the derivative of 10x is 10, right? Does that make sense? But now here we go. And so there's going to be my looking of my answer, but I got to have this condition right here. See, the first derivative is non-zero, so this checks, this checks. Now, f of 5 has got to be 15. F of 5 equals 15. That's going to allow me to solve for the constant. So in place of, so f of 5 would be a constant times 5, but that's equal to 15. What does that make the constant equal to if I have 5c equals 15? Divided by 5, you got it. C equals 3, and therefore my answer, 3 dots in a triangular fashion, means therefore the actual function is constant times x, and that constant is 3. The answer is 3x. It's detective work in terms of understanding the relationship of derivative. And that's the key right there. With the second derivative being 0, that forces the first derivative to be a constant, which means the original function had to be a constant times x. So you get all the way down to the second derivative being always 0. And now with that initial conditions, what it's called, f of 5 equals 15, you can actually figure out what the constant is. There's only one answer. F of x is equal to 3x. Does that make sense? All right. Now, that second derivative test I was just talking about earlier, that's from this particular section here. So, let's take a look at it. Now, remember what I said about the second derivative test. The whole purpose of the second derivative test is to tell you about your max min points. So to figure out if you got a max min point, you got to take that first derivative, set equals 0, and solve. Okay? So the second derivative test, in essence, is this. You got to find your critical values by taking the first derivative, set equals 0, and solve. And don't forget, and where the first derivative does not exist at. And then there were two cases. So this is the second derivative. This is called the second derivative test. Second derivative test. Case 1. If the second derivative at your critical value is greater than 0, that means it's going to be concave up. That means you're going to have a local minimum. In case 2, if the second derivative at your critical point, we'll call it C equals critical value there, at your critical value is less than 0, that means you're going to be concave down. That puts the point at the top, which means you're going to have a local maximum. And what the purpose of the second derivative test is, I didn't have to draw a number line to figure out who's the max and who's the min. So here we go. In terms of this, here's your learn mode. Suppose that f's a function, f prime and f double prime exist on the interval between a and b, and c is inside that interval between a and b, such that f prime of c equals 0. That means c is my critical point. If f double prime of c is greater than 0, then f of c is going to be what? Greater than 0 means it's concave up, so what kind of point am I going to have? Local minimum. If f double prime of c is less than 0, then less than 0 means I'm concave down. That puts the point at the top, means I'm going to have a local maximum. However, there's one problem. You can either be greater than 0 or less than 0, but there's one other possibility. And that is if the second derivative at c there, I should put a plug in c in this thing, is actually equal to 0, that means it's not going to be a maximum or minimum. This quote-unquote second derivative test fails because it's actually going to be more likely to be an inflection point. Okay? Number 2, if f double prime is defined on a local maximum at the point c, f of c, a curve is which way? Okay, if you have a local maximum, maximum is going to be at the top. What kind of concavity do you have? Concave down. We're down over here. Concave down. So it makes sense? And similarly, if f double prime of c is defined at a local minimum, being a local minimum, it's going to be like this. terms of the concavity, the curve, talking about the concavity, this is going to be concave up. Now, and this is the comparison between the two, so they're trying to emphasize this. The second derivative test requires only one number to be checked. All we got to do is plug one number into my second derivative. And if it's positive, it'll be concave up, it's a minimum. If it's negative, it'll be concave down, it's a maximum. Okay? The first derivative test, to actually do that, you had to do the number line. And you had to check a point, you had to do test values on either side of your critical value. So you had to actually check two numbers to be computed. So it's quote-unquote more efficient to do the second derivative test than the first derivative test. But if they tell me, hey, to use intervals of increase and decrease, well, I don't need to do the second derivative test. I can tell you from the number line of the first derivative test whether it's a max or min. But if you just give me a critical point and we need to tell you quickly if it's a max or min, use second derivative test. Just plug in a second derivative. If it's positive, concave up, it's going to be a minimum. If you plug in a second derivative, it's negative, it's going to be concave down, it'll be a maximum. It's much quicker. All right, now, from a business perspective, the point at which sales continue to increase, but at a slower rate, is called the point of diminishing returns. The point of diminishing returns. Okay? Now, if you look at this point of diminishing returns, a point at which the sales continue to increase, you're making money. Your sales are going up. But going up, I mean, we're talking about slope. But what's going on here for diminishing returns is it's going up, but you're concave up, and then you hit to that concave down aspect of your problem here. This is that point of diminishing returns. I'm going from concave up to concave down. What does that concave down mean? Eventually, I'm beginning to, my sales they're still increasing, but they're not going to be increasing, quote unquote, as fast. That's the point of diminishing returns. And so this is what it looks like. And so when you analyze this, the point of diminishing returns occurs at a point of inflection. Okay? Point of inflection is where you change concavity. Notice I'm going from concave up to concave down. Well, sales change from, and that's it, concave upward to concave downward. That going into, this is a very special case from sales. You're going from being concave up to concave down. So you're going from plus, so if you look at your number line on the old second derivative test there, second derivative number line, here is your A, your hypercritical value, your inflection point. You're going from concave up to concave down, and it has to be in this direction, positive to negative. That gives you that point of diminishing returns. This is what's going on. So there's some interesting terminology for your business group. Okay? So, turn page. So let's take a look at this example here from the old hawkstv.com thing there. So please go watch the video as well on Hawks. They made you one just to do, but they use different numbers than we do, but the same concept here. Got two parts of this one. It says, find the second derivative of x, and then use the second derivative to locate any max minimum points of your graph. All right, so two things here. You got to find the second derivative. To be able to find the second derivative, you got to go to the first derivative first. So I got to have my first derivative. So on your mark, get set, go. F of x is equal to 4x cubed plus 12x squared minus 180x. What's your first derivative? First derivative is going to be 12x squared plus, the derivative of 12x squared is 24x minus the derivative of 180x is 180. And then you're supposed to find the second derivative. The second derivative of 12x squared is 24x plus derivative of 24x is 24, derivative minus 180 is 0. So I got 24x plus 24. So that is my second derivative. Answer the question, circle it, type it in Hawks there. Now, here we go. Use the second derivative to find any local maximum minimum points. So here's the deal. I gotta find critical points first. Where are my critical points gonna be at? To find a critical point, you've got to take that first derivative, which is at 12x squared plus 24x minus 180, set it equals 0 and solve. So that same stuff we did in chapter 3 is going to continue to haunt you. To maximize or minimize, you take derivative, you set it equals 0 and solve. In this problem, I can factor out a 12. That gives me x squared plus 2x, and taking a 12 out of 180 is 15. And now I'm going to factor x, what times what is 15? That subtract that to be 2, 5, and 3. And because it's minus, opposite sign, since the middle term's plus, plus on the 5, minus on the 3. Set it equal to 0 and solve. Set each factor that has an x in it equal to 0 and solve. And I get x equals -5 and x equals 3. So we're talking about these are C, and I'm emphasizing the P word. What does P stand for? Point. To have a point, I got to have a y coordinate. So I've got my critical values. They are -5 and at 3. You with me? But how do I get that y coordinate? What am I going to do? I'm going to do f of -5, and I'm going to literally use my calculator, plug it in here, and I'm going to use f of 3. So here we go. F of -5. That'll be 4 times -5 cubed plus 12 times -5 squared minus 180 times -5. I'm literally just plugging in on my calculator to get the y coordinate, 700. So -5 is 700, so the point is -5 comma 700. And now I'm going to plug in f of 3. So this will be 4 times 3 cubed plus 12 times 3 squared minus 180 times 3. I get -324. F of 3 is -324. This is how you get your y coordinates. Does that make sense? But now, here's the big deal. I'm going to use the second derivative test. So, which one's which? I'm not going to look at a number line. I haven't even drawn a number line on this thing. This is what I'm going to do. I'm going to take my second derivative, and I'm going to plug in -5. My second derivative is 24x plus 24. That'll be 24 times -5 plus 24. And just to show you on the handy dandy calculator, 24 times -5 plus 24 is -96. I don't care what the number is. It's negative. That means I am concave down, which puts my critical point where? At the top. So at -5, comma 700, that is going to be a local maximum by the second derivative test. I'm just analyzing my second derivative. And the other one, f double prime of 3, that'll be 24 times 3 plus 24. 24 times 3 plus 24 is a positive 96. I don't care what the number is, it's positive. That means I'm concave up, which puts my critical point at the bottom. This is going to be a local minimum. That is identifying using the second derivative test. Does that make sense? And I didn't have to use number lines on that. Any questions on that? So, and this is the answer, and this is the work involved. So, take a look at your practice. Find the second derivative of each function and use it to locate any maximum minimum point. So, pretty much more of the same. So, let's take a look at this guy here. I'm going to take my first derivative. Derivative of x to the fourth is 4x cubed. Minus derivative of 32x squared is what? 64x. Derivative minus 10 is 0. Now I'm going to take the second derivative. Derivative of 4x cubed is 12x squared. Minus derivative of 64x is 64. So there's my second derivative. But to actually find the critical values, I'm going to take my first derivative, which is 4x cubed minus 64x. I'm going to set it equal to 0, and I'm going to solve. I got to find my critical values. Same thing as what we did in chapter 3. Now on this one, I can factor out something or other. 4x cubed minus 64x. What can you pull out of this guy? I can pull out an x, and I can also pull out a 4. Makes it a little bit smaller. That's going to give me an x squared minus, I'm pulling a 4 out of 64. 64 divided by 4 is 16. And now, the x squared minus 16 is the difference of squares. I can factor that guy out to become x plus 4 times x minus 4. And now I'm going to set each factor that has an x in it equals 0. So 4x equals 0, x plus 4 equals 0, and x minus 4 equals 0. That's going to give me three critical numbers. X equals 0, x equals negative 4, and x equals positive 4. Divide by 4, subtract 4, and then add 4. So these are my critical values. Does that make sense? Now, what about so I'm supposed to find the max min points, so critical points are going to be 0, comma, something or other, negative 4, comma, something or other, and positive 4, comma, something or other. What am I going to do to this guy? To get my y coordinates, what do? I plug them into the original equation. Well, I can do 0 without a calculator. Plugging in 0, I get what? 0 to the 4th minus 32 times 0 squared, applying minus 10 is minus 10. Plugging in 4, negative 4. Plugging in negative 4, that'll be negative 4 to the 4th, minus 32 times negative 4 squared, minus 10. That gives me negative 266. And plugging in positive 4 on this thing gives me the same negative 266, by the way. Does that make sense? I literally plugged into the original function to get these guys. Now, let's use our second derivative test. What is f double prime of 0? Now, over here, here's my second derivative right here, so I'm going to plug it in. I don't need a calculator for this. 0 squared is 0 times 12 is still 0 minus 64 is negative 64. I don't care what the number is. What's the sign of it? Negative. And on the second derivative test, this measures concavity. A negative second derivative means it's concave which way? Down. Second derivative down, which puts the critical point at the top, which means this thing's a what? Local maximum. This concept of understanding that the second derivative measures concavity, and just draw it. Concave up is U-shaped up, that's when it's positive. Negative second derivative is concave down, and then just identify where the max min point is going to be at. It's either going to be at the top or the bottom. So here, my critical value is negative 4. So when I plug in negative 4 into my derivative, this will be 12, and I'll put it on the calculator for you guys. 12 times negative 4 squared minus 64. So I'm plugging negative 4 into my second derivative, and I got 128. I don't care what the number is. It's a positive number. That means it's concave up, which means what do I got at the bottom of this guy? This one's going to be a local min. And then if I take the second derivative of positive 4, plugging in positive 4 on this thing, well, no problem, just recall it back down and just change that negative to a positive. Yeah, when you square negative, it's still positive. I'm going to get the same number, 128. But it's still a positive second derivative, means it's concave up. So this guy is also going to be a local minimum. So in this problem, I've got 2 local minimums and 1 local maximum. There's my answer, using the second derivative test. And notice, most important, I didn't draw a number line to analyze this. I could have, but it would have taken a little bit longer, more evaluation stuff I have to use. Questions? All right, take a look at the next problem. How nasty can they make it? Well, let's take a look. Okay. F of x equals x squared minus 32 times the square root of x plus 1. Well, first thing I got to do is clean this guy up. This is x squared minus 32 times x to the 1/2 power plus 1. And so, first thing I'm going to do is going to take my first derivative. My first derivative is, derivative of x squared is 2x minus, what's derivative of 32x to the 1/2? Well, half of 32 is 16x to the negative 1/2. And derivative of 1 is 0. And now I'm going to go ahead, while I'm at it, just go ahead and take the second derivative. Derivative of 2x is 2. Derivative of minus 16x to the negative 1/2. Negative 1/2 of negative 16 makes it a plus 8x, subtract 1 to the negative 3/2. But I am going to go ahead and clean up both of these two derivatives. But this is the first derivative and the second derivative, but now I'm going to have to solve some stuff. So negative exponents go where? To the bottom. This is an individual little term, so it's going to go to the bottom of that term. So this will be 2x minus 16 over, and a half of power is the square root of x. And my second derivative is going to be 2 plus 8 divided by x to the positive 3/2. So it just goes to the denominator. That's cleaned up. Does that make sense? Now, how do you find your critical values? What am I going to do? I'm going to take my first derivative, I'm going to set it equals 0 and solve. And don't forget this, where the first derivative does not exist at. Look at your first derivative. It is 2x minus 16 over the square root of x. First off, you can see a point where the derivative doesn't exist at. Where does the derivative not exist at? 0. The derivative does not exist at x equals 0. Square root of 0 is 0, but you can't divide by 0. X equals 0 is going to be a problem with this first derivative. Does that make sense? And then the other one, I'm going to take the rest of the function, 2x minus 16 over the square root of x. I'm going to set it equals 0. I'm going to move this term to the other side. So 2x equals 16 over the square root of x. I'm going to multiply by the square root of x on both sides. So it'll be 2x times the square root of x is equal to 16. But remember, square root is a half a power. And x to the first times x to the half is x to the 3/2 equals 16. Divided by 2. I get x to the 3/2 is equal to, 16 divided by 2 is 8. And what kills off a 3/2 power? Raising it to the reciprocal, which is 2/3 power. So x is equal to 8 to the 2/3 power. And remember your powers, you can put this on the calculator as well. The numerator is your power, your denominator is your radical. What is the 1/3, which is cube root? What's the cube root of 8? 2. What's 2 squared? 4. 8 to the 2/3 power is 4. 8 raised to the 2/3 power is 4. So in this particular problem, I got two numbers. I got x equals 0 and I got x equals 4. To find the, quote, critical value of points, I'm going to plug these numbers into the original function right here. And plugging in 0 is absolutely not a problem here. Plugging in 0, I end up getting 1. And plugging in 4, when I plug in 4, I end up, let's see here, square root of 4, I get negative 140, I get negative 47. Just go ahead and stick on my calculator, it's easier. Okay, now, second derivative test, what happens? Look at this point right here, second derivative. What is the second derivative of 4? Plug it in. That'll be 2 plus 8 over 4 to the 3/2 power. I'm going to put that on the old calculator just for expediation here. 2 plus 8 divided by 4 to the 3/2 power is 3. I don't care what the number is. What's the sign of it? It's positive. That means it's concave up, which means this guy's a what? Local minimum. Watch this guy. When I plug in 0, I get this. I get f double prime of 0. And what's f double prime of 0? That'll be 2 plus 8 over 0 to the 3/2. What are you not allowed to divide by? 0. This thing does not exist, so my second derivative test is not going to tell me anything about this particular point. You're going to have to graph it and figure out, because it's a square root, your domain is x is greater than or equal to 0. This thing ends up becoming you basically end up having to graph it, but from the local, you only have a local minimum particular problem here. This is just going to be, quote unquote, an endpoint, not an actual critical point. Does that make sense? You've got to be able to plug it into your second derivative to be able to use the second derivative test. This tells you nothing. It's just going to be an endpoint. We'll do more of these problems next time on Friday and finish this stuff up and then move on into section 4.2. So study hard on this stuff, and I'll let you guys know more about the review sessions on Friday on Friday's class. So see you guys then.